All right, welcome everyone. Let's get started. So today we're going to start talking about a really important topic. And so if you go into Calc 2, you're going to see this over and over and over again, and then in Calc 3 you'll see it over and over and over again. So this is going to be an incredibly important topic that we're going to just start talking about today, and it's substitution rule. So learning outcome I3 is going to be, we're going to see how to calculate an indefinite integral using this substitution rule. And then if we get to it in learning outcome I4, we'll see how to do definite integrals involving substitution rules. So very, very important topic. So let's get started. And the first thing we're going to start with is going back to derivatives. So we're going to go back to our chain rule. And let's just kind of mention why in a second, but let's just recall what the chain rule says. So it tells us how to differentiate the composition of two functions. And a lot of times when we talked about the composition, we would call one of the functions the outer function. And then a lot of times we saw parentheses, and the function inside the parentheses we called the inner function. And so the chain rule allowed us to differentiate composite functions like this, where there's an outer function and an inner function. So what does the chain rule say? Well, the derivative of f composed with g of x is equal to the derivative of our outer function with the inner function plugged in times the derivative of the inner function. And what we're going to do is we're going to basically prove the chain rule or the substitution rule for integration using this chain rule. And so when we as we're kind of developing our integration techniques, what we're going to see, and what we've kind of already seen to some degree, is that most of the derivative rules that we've learned, so sum, difference, constant, multiple, product, chain rule, they all have an analogous rule for integration. And that's what we're going to see here with substitution rule, is it's really like the opposite of the chain rule. So chain rule is for derivatives, substitution rule is going to be kind of the opposite for when we do integrals. And we're going to kind of prove that here. So let's start with the our composite function. So f of g of x. And what does the chain rule say? So let's just write down what the chain rule says. And what we're going to do is we're going to apply the integral to both sides of this equation. So we're going to integrate both sides. So we'll integrate the, you know what, I need a little bit more room. So let's integrate the left side. And that just gives us the integral of a derivative. And then we put our dx at the end of the integral. And we're going to do the exact same thing on the right. So we're going to integrate the right side. And if we notice, when we integrate a derivative like we have here, the integral and the derivative, they're kind of reverse processes, so they cancel out. So the integral and the derivative cancel. And they cancel because this derivative is being applied to the entire term on the left side there. So it's not going to quite cancel out on the right side because it's not an entire derivative. So, you know, on the left there, it's the integral of everything's being differentiated, so we can cancel out. And so when we do that, we're going to get f of g of x plus c on the left, and then this integral on the right. And this is basically what substitution rule is going to say, is that we can calculate that integral on the right, and it confirms that we should get that answer, f of g of x on the left. So let's look at what the chain rule, well, actually, before we get to the chain rule, there's this gadget that we want to define that shows up right here at the end of this integral here, this g prime of dx. And it has to do with an idea of differentials. So before we actually get to the substitution rule, we're going to kind of just talk a little bit about the definition of a differential. So let's let u equal to g of x be a differentiable function. Then we define the differential du as du is equal to g prime of x times dx. So here we're thinking of dx as sort of like a variable. So we're going to differentiate our function and then multiply by dx. And so dx we can think of as just it's just like a variable. So, you know, it's a variable with two letters in its name. So normally we use things like x and y and u and theta and t. Dx is just a variable just like that. It just has two letters in its name. So our process, if we have a function u equal to g of x, the process for calculating the differential is we differentiate the right-hand side like usual, multiply the result by dx, and that's our differential du. So as a little example, let's calculate the differential for u equal to x squared plus 1. The differential in this case, du, is going to be the derivative of x squared plus 1 times dx. And again, think of dx as just like a single thing. It's just a variable with two letters in its name. All right, so what's the derivative of x squared plus 1? Well, it's 2x. So du in this case is 2x times dx. So note, du does not equal 2x. There's a little bit more. We need the dx to be part of the differential there. All right, so let's see why this is going to be important when we get to the substitution rule. So our substitution rule is really telling us how to integrate a kind of the result that we would get from the chain rule. And we're going to think of this substitution rule as really, it's sort of more like a process, but let's just read through the results. So let's suppose that we have an inner function u equal to g of x, and it's differentiable. So we know we can differentiate it. And we know our outer function f is continuous. Continuous just makes it so that we know we're not running into any issues of composition, things being undefined, things like that. So what the substitution rule says is the integral of f composed with g of x times g prime of x is equal to the integral of f of u du. And so what we're doing here is really like a change of variables. We identify what the inner function is, and then we do a change of variables based on that. So what we're going to do is we're going to let u equal g of x. And this is our inner function. So we're going to let u equal the inner function. And then once we've figured out that, we're going to calculate du. And this is our differential. And do it how we just explained. So du is equal to derivative of g times dx. Again, dx, we can think of it just like a variable, two letters in its name. And so really what we're doing, ultimately what we're going to do here is we're going to change the variables in our integral. So how are we going to do that? So this is the integral that we're interested in calculating, and it's going to be kind of complicated looking. So it's going to be this complicated integral. It's not one of our basic forms. It's not an elementary form that we could just go to a table and look up. So what we're going to do is we're going to simplify it down by changing the variables. So this, in particular, this g of x term that we see inside, well, that's going to become u. So that's going to become the u that shows up right in here. And the g prime dx that we see in the rest of our integral, well, that's going to become the du. And because we know g prime of g prime times dx is equal to du by our calculations. So we can take this complicated integral that we're trying to solve there on the left, and by changing the variables, produce something that's easier. And that's our ultimate goal here. When we apply the substitution rule, is we're going to be presented with a complicated integral that we see there on the left. And when we do the change of variables, the substitution, it gives us an easier integral, so something that's closer to one of our basic forms. So substitution rule, if we do it correctly, hopefully it returns an easier integral. So that's ultimately the goal here. That integral on the right should be something we can do. So this is the formula. This is the statement for substitution rule. But like I said, we generally think of it more as a process. And so let's see an example of how this process works. So we're going to do the integral of 3x plus 4 all raised to the power 10 times 3 dx. And we're going to see how substitution rule works. So our first step is to choose u, and then once we've figured out u, to calculate du. And so kind of our guiding principle for choosing u is it should be the inner function. And so we see kind of parentheses, and inside those parentheses we have 3x plus 4. So that's going to be step one. We're going to let u in this example be 3x plus 4. It shows up inside those parentheses. So once we choose u, then we calculate du. So basically, forget about your integral for a second, and let's calculate, and hopefully I can get that back, and let's calculate du. So forget about everything else that's in your integral, and we're just going to do the derivative of 3x plus 4, so it's 3, and then we multiply that by dx. So that's our differential du that we calculate based on whatever we chose for u. All right, so that's our first step, is to choose u and then calculate du. All right, so now in step 2, we're going to take those two gadgets that we have there, u and du, and we're going to substitute those into the original integral. So we're going to change over the variables. And so in particular, the 3x plus 4 that I see right in here, that's going to become u. And then the 3dx, that's going to become du. And this is a nice example. That's a perfect match. Normally we don't always get quite a perfect match like that. So, but in this example, it's our first one. So it's a nice substitution. Everything fits perfectly here. So step 2 is to take our u and du and just substitute them in. So we're going to have the integral of u raised to the power 10 instead of the 3x plus 4 raised to the power 10. And then that 3dx there at the end is going to become du. And so what we've done is we've taken a complicated integral that was not one of our elementary forms. It wasn't a basic power function. It's not something, it's not the sum or anything like that. It's a more complicated integral. And what we've done by doing this change of variables is we've produced an integral that's pretty basic, something we can do with one of our, basic derivative or antiderivative rules. So integral of u to the power 10, that's just basic power rule. So we can finish this off. And that's what the step 3 is to just do the integration. So what's the antiderivative if we apply the power rule? Well, our variable is u. We add 1 to the exponent. And then we take that new exponent, flip it, put it in front. So the antiderivative is 1 over 11 times u to the power 11. And then we put plus c at the end. So that's kind of our standard integration stuff we looked at in the last lecture. And then the very final step is we need to convert back to our original variable. So we started with an x, we want to convert back to x. And so the way to do this is to look in our antiderivative, and wherever we see a u, we're just going to plug in 3x plus 4. We're just going to convert back. So we'll have the 1 over 11 in front, and then we'll have our 3x plus 4 now raised to the 11. And then we still have our plus c there at the end. So, and that's it. That's our antiderivative. So that's really how substitution rule works. The chain rule is where it comes from, but we think of this as more of a process. It's kind of these 4 steps. And so the difficult thing about this is it's up to us to figure out what u is. And so the tricky thing about integration, and you really see this in Calc 2, is that there's not always a clear path for how to go about doing the integration. So for our purposes with substitution rule, the difficult part comes from how do you pick u. And so kind of introduce just a few different strategies as we go through the lecture today and next time. But kind of the main strategy is you're looking for an inner function. And so you want to have just some of the basic antiderivatives in mind when you're looking at these problems. So what are some of our basic antiderivatives? Well, we have power functions. So the integral of u to the power n is, we just do power rule. So u to the n plus 1, flip the new exponent, put it in front. So 1 over n plus 1. This works for everything except when the exponent is negative 1. If the exponent is negative 1, well then we have basically a different rule that tells us what the antiderivative is. So u to the negative 1, the antiderivative of that is natural log absolute value u. Then we also have exponentials. If we have e raised to the power u, the antiderivative is just e raised to the power u. And then we might have trig functions. So something like sine of u, what's the integral of sine of u? Well, it's negative cosine of u. And so when you're presented with an integral, you kind of want to keep these basic antiderivatives in mind, and they're going to guide you on how to, hopefully, you should choose u. So if you see something inside parentheses all raised to an exponent, so you see something complicated raised to a power, well, what you should try is let u equal the terms inside the parentheses. And that's what we just had in that last example. We saw, what did we see? We had 3x plus 4 inside the parentheses, so we let u equal 3x plus 4. So you let u equal the term that's inside the parentheses. And that's really kind of the main strategy, is when you see parentheses, that should be your choice for u. Now, what if we have a fraction? Well, the fraction, if you see something complicated in the denominator, you let u equal the term in the denominator. So you let u equal the terms that are inside the denominator. And this is just going back to those basic formats, those basic antiderivatives. The integral of 1 over u, well, if we see something complicated in the format 1 over something, well, let's let u equal the terms that are inside the denominator. One little exception to this, one little caveat, is only if that has an exponent 1. So it might be like no visible exponent. We don't normally write an exponent of 1. If it was like a raised to the power 2 or raised to the power 3, well, then you just kind of go back to our usual strategy. You write it as a negative exponent. And then you have something inside a power with a negative exponent, and you're back to just identifying what's inside the parentheses. All right, so if we have a power function, terms inside parentheses. If we have a fraction, we might choose let u equal what's inside the denominator. If we see an exponential function and there's something complicated in the exponent, well, then you let u equal what's up there in the exponent. So you let u equal the terms that are inside the exponent. So u is always, well, for the most part, it's going to be the inner function. It's inside something else. Same thing, if you see a trig function and you see some complicated terms inside that trig function, again, we're letting u equal the terms that are inside the trig function. So, you know, if you have an integral and you see parentheses and then there's something complicated inside the parentheses, that's going to be our first choice for u. Now, unfortunately, this isn't always going to work. So this is kind of more of a rule of thumb type loose strategy. Sometimes you have to get creative. But for the most part, in a lot of the examples we're going to see, this is kind of the approach to take. So let's try doing the integral of 2x e to the x squared dx. And we have to figure out what we should choose for u. That's the very first step. before we do anything else. So when we look at this, you kind of want to look at the individual pieces of the function. And you want to look at you want to try to identify what the most complicated piece is. So if I was looking at this, I would think e to the x squared is the more complicated piece. And what we have here then is something e raised to something. And the term in the exponent there is, it's not just x. There's more to it. It's x squared. So we see that we have this e raised to the something format. So we're going to let u equal the term that's inside the exponent. So we're going to let u equal the x squared. All right. Now, once you identify that complicated term, well, we'll back up. Once you have an idea what u should be, then immediately you calculate du. So for right now, let's put that integral out of mind. We have u equal to x squared. Let's calculate du. And we don't want to. So du is the derivative, so 2x, and then we multiply by dx. All right. So the goal is, so that's step one. Figure out what you should pick for u and then calculate du. Now we're going to plug all of that in to our integral in step two. And to kind of help with that, not always necessary, but it can be helpful to take any loose terms that you have here. So like this 2x, the e to the x squared was kind of our main focus. So take any of the other terms that you have just kind of floating around in the rest of your integral and kind of put them all together next to the dx. So we'll have our e to the x squared first, then we'll put our 2x, and then at the end we'll put our dx. So this isn't absolutely necessary, but it can be helpful to just kind of put all those extra terms next to the differential. At least when you're first getting started doing these problems. You know, once you get the hang of this, that won't be necessary. But at least at first, that's a helpful thing to do. And you don't want to move them outside the dx. So the integral sign and the dx sort of form like bookends. So the integral sign and then the dx tell you to do the antiderivative of everything in between. So we don't move anything outside of them. Everything should stay inside. All right. So now, with that in mind, we're going to substitute u and du into this integral. And so if we look at this, the x squared that we put up there, well, that's going to become u. And then the 2x dx that we have kind of left over in our integral here, well, that's nice. It's precisely what we calculated du is. So again, that's not always going to be a perfect match like it is here, but, you know, we're still getting used to this, so it's a nice perfect match. So this is going to become exactly du. So step two then is to just plug everything in. So we're going to have the integral, instead of e to the x squared, it's going to be e to the u. And then instead of the 2x dx, it's going to be du. And so we've taken this complicated integral, and we've got it to a point now where this is something that's, you know, just we can look up. We know this one. We have this one memorized. So the antiderivative of e to the u is just e to the u plus c. And that's step three. just calculate that new integral in terms of your variable u. And so when, and I think someone asked here, let me just go back. Yeah. So when you do the antiderivative, so someone had the question, what happens to the du? When you find the antiderivative, the integral sign and the differential are gone. So in step 3 here, when you actually find the antiderivative, you don't keep writing integral sign and you don't keep writing the du. So when we find the antiderivative, the integral sign and the differential are gone. Same thing for just doing a regular integral. So even if we weren't doing substitution rule, that same idea would apply. Same thing for derivatives. So if we had the problem, say, d dx of x squared, when we actually calculate the derivative, we don't keep writing d dx. It's just the derivative is equal to 2x, and that's it. So same thing goes with antiderivatives. Once we find the antiderivative, we don't keep writing the integral sign, and we don't keep writing the differential. So that's a very good question, because that is a common issue that I see is people will do antiderivatives, but I'll still keep seeing integral signs and du's floating around. So as soon as you do the antiderivative, integral sign's gone, du is gone. All right, we're not quite done. So we have the antiderivative right now as e to the u plus c, but our original function had x's, so we want to get back to x. So that's step 4. So step 4 is to just convert back. So wherever I see a u in my antiderivative, I'm going to change it. And I'm going to change it because I know u is equal to x squared. So wherever I see a u, I'm going to replace that with x squared. And that's it. So that's my antiderivative. Now the nice thing about doing antiderivatives is we can always check our work. And so the way we check our work is we take our answer. So we take the function we got as our answer, e to the x squared. I'm not going to do the plus c because we know derivative of constant is 0. But we take the kind of the main part, the variable part of our antiderivative, and we differentiate it. And if we did everything correctly, we should get back our original function that we were trying to integrate. And so that's the nice thing about doing integration is we can always check our answers. And so if you have to use substitution rule in your work here to get the antiderivative, well, when you're checking your answer, you're going to have to use the chain rule to differentiate. So that's what we're going to see here. Let's check. Let's take our answer, e to the x squared, and we're going to differentiate it. So we're going to apply the chain rule, or really the special case of the chain rule, which we called the general exponential rule, which said the exponential part stays the same, and then we take the term that's inside the exponent and we differentiate it. So derivative of x squared is 2x. So we end up with e to the x squared times 2x. And we see that, yeah, that is what we started with. The 2x was in front, but that's okay. So, we can always check our answer. And for these substitution rules, when you check your answer, you're going to have to use chain rules somewhere along the way. All right, let's try another one. So it really comes with practice. So let's look at the function 3x squared over x cubed plus 1, and we want to evaluate this integral. Now, first thing we think is this something, is it one of our basic forms? So is it something I could look up? And it's not. So we have to use substitution rule. It's more complicated than that. And so when you're kind of presented with these functions and it's not necessarily clear, you know, what you should pick for you, it's going to be helpful. So just little tips and techniques to pick up along the way. It's going to be helpful to kind of separate this function into its, you know, separate parts. Again, not absolutely necessary, but if you're kind of stuck on a problem, this might be something helpful to try. So what I mean by this is I'm going to write this integral instead as 1 over x cubed plus 1 times 3x squared, and then the dx at the end. And so I've separated my fraction, numerator, and then 1 over the denominator. And so when I look at this, I kind of go to the more complicated piece. So I have a couple different pieces to work with here. I focus in on the more complicated piece. And what I see is, I would say that it's the fraction. So what we have here, if we go back to our list of basic forms, is we're seeing something like 1 over some terms. And so what we're going to do is we're going to let u equal those terms that are inside the denominator. So this is sort of our 1 over something format. So we're going to let, in step 1, we're going to let u equal those terms that are inside the denominator. Then, forgetting about the integral for a second, we're going to calculate du. So derivative of x cubed plus 1 is 3x squared. And then we multiply by dx. That's step 2. And then we kind of go to our integral and see what we have to work with. So we already know that 1 over x cubed plus 1, that's going to become 1 over u, kind of by design. And then the 3x squared here that we had left over, together with the dx, well, that's a nice perfect match. That's exactly what we calculated for du. And so this is going to become du. So the 1 over x cubed plus 1, that becomes 1 over u. And then the 3x squared dx, that becomes du. So that's step 2, is just to take those different pieces, u and du, and try to fit them into your integral. Substitute them in. And once you've done that, now this is a basic format that we can just integrate. So the antiderivative of 1 over u is natural log absolute value u plus c. So that's step 3, get the antiderivative. And then finally we want to get back to x. So that's our last step, is to just plug in wherever we see a u in our antiderivative, we're going to plug in x cubed plus 1. So it'll be the natural log of x cubed plus 1, natural log of absolute value, x cubed plus 1 rather, plus c. And that's our final step, just to convert back to the original variable. So, you know, nice thing again, anytime we want to differentiate or anytime we want to check our answer, we can just differentiate and we should get back to where we started. So we can check our work here and just take our answer, which was the natural log of absolute value x cubed plus 1, and just differentiate it. And if we did everything correctly, we should get back our original function that we started with. And so we had to use substitution rule along the way. So when we differentiate, we would need to use chain rule. And we had kind of a special case of the chain rule, which we called the general log rule, which said how you differentiate the log of something is you do the reciprocal of what's inside, so 1 over x cubed plus 1, and then you multiply by the derivative of that inside function. So derivative of x cubed plus 1. And the derivative of x cubed plus 1 is 3x squared. And that's precisely what we started with. The 3x squared was on top, but that takes us back to what we started with. So along the way there, we had to use our chain rule. So you can kind of see, when we first talked about chain rule, why we stressed, I want to see those steps of you applying the derivative to the inner function is because it comes back when we're talking about substitution rule. And so being able to identify that inner function is going to be kind of the tricky thing here. All right, let's try another example. So substitution rule is incredibly important. If you're going on to Calc 2, you have to be able to do substitution rule. You're going to have a bad time if you can't do substitution rule. So as many examples as we can get through, and as many problems as you can practice, the better off you'll be for our course, but then also in Calc 2. Let's try another one. Integral of the square root of 4x plus 5 dx. And before we do anything, we should use our common strategy. Whenever we see a root function, we know we're going to be doing power rule at some point in some format. So instead of having a root function, let's write it as a power function. So we're going to write this instead as 4x plus 5 raised to the power 1/2. That's something we would do regardless of whichever technique we would use. But doing that, we see parentheses, and then we see something complicated inside those parentheses. So that's telling us what we should pick for u. So we see that we have here the format of something raised to the power n. So for step 1, we're going to let u equal what's inside the parentheses, the 4x plus 5. All right, so put the integral out of your mind for a second. And this is where we're going to see things don't always match up perfectly. So let's forget about the integral for a minute here. We've chosen what u is. Let's calculate du. So it doesn't matter what's going on in our integral. Let's just calculate du. So derivative of 4x plus 5, derivative of 4x plus 5 is just 4, and then we multiply by dx. All right, so let's see what we have if we compare it to our integral. So when we look at this thing, we only have a dx there at the end. So that only matches up with the dx here. But that 4 is something extra. So we have this extra constant term that doesn't appear in our original integral. And so the way we handle this, so you always want to compare your differential to what you have in the original integral. And for the examples we'd seen so far, everything was a perfect match, but that's not always the case. And that's what we're seeing here. So we have this extra constant when we calculate the differential du. And the way we handle this is we're going to solve for dx. So we're going to take that equation du is equal to 4dx, and we're going to solve for dx. So again, think of du, think of dx. These are just variables with 2 letters in their name instead of 1 letter. So when we solve for dx, what I would do is I would divide both sides by 4. So on the left, I would get 1 over 4 times du, and then on the right, I get dx. So I've solved that equation, du is equal to 4 times dx. I solved it for dx. And now, what I see here is I've solved for all the terms that I have, and now we have a nice match here. So when I go into step 2, where I'm going to start substituting these gadgets into my integral, well, that 4x plus 5 raised to the 1/2 power, that's going to become u to the 1/2. And that's because I'm saying, all right, this 4x plus 5, that's my u. So I have u to the 1/2. And then my dx there at the end, that's going to become 1 over 4 times du. So I get this simplified integral of u raised to the 1/2 times 1/4 du. And that's what we're trying to do now. So I've substituted in those values. That 1 over 4 now is just a constant multiple. So maybe to help us out, we can move that in front of the integration. So we can move constant multiples outside of the integral sign. So that becomes just 1 over 4 times the antiderivative of u to the 1/2. Again, you don't necessarily have to show that step, but for right now, that might be helpful. And we just want the antiderivative of u to the 1/2. So now we integrate just like we normally would. So the 1 over 4 stays in front, just a constant multiple. And then our variable is u, so we write down u, add 1 to the exponent, bumps us up to 3/2, and then we take that new exponent, flip it, put it in front. So we put a 2/3 in front. And then plus c. All right, so that's the antiderivative. We want to get it back in terms of x. And maybe before we do that, maybe we simplify a little bit. So we have 1 over 4 and then 2 over 3 in front. So if we simplify that, we end up with 1 over 6, u to the 3/2 plus c. And then our very last step is to convert back to x. So basically, wherever I see a u, I'm going to change that back into 4x plus 5. So I'll have 1 over 6, 4x plus 5 raised to the 3/2 power plus c. And that's my antiderivative, so that's my answer. And the nice thing about doing these integral problems is we can always check our work, and we can check it by just taking that answer, the 4x plus 5 raised to the 3/2 power with the 1 over 6 in front. Again, don't worry about the plus c because we know when we differentiate, which we're going to do to check ourselves, derivative of a constant is 0. And so we had to use substitution rule. So when we do the derivative to check our work, we should use the chain rule. And in this case, we're going to use what we called the general power rule, which was just a special case of the chain rule, which said basically bring down the exponent keep what you have in the parentheses exactly the same. Subtract 1 from the exponent, so we go down to 1/2. And then take those terms that are inside the parentheses, the 4x plus 5, and multiply by their derivative. And so the derivative of 4x plus 5 is just 4. And so what we end up with then is if we multiply the 1 over 6, and I won't go, the 1 over 6 times 3/2, that simplifies to just 1 over 4. And then the derivative of 4x plus 5, that's just 4 as well. So the 1 over 4 and the 4 would just cancel, and we're left with then 4x plus 5 raised to the 1/2. And that's exactly the function that we started with trying to integrate. So this does check out. All right. So again, you don't have to check your work always, but if you want to check your work, do the derivative of your answer, and you should go back to where you started. All right. Let's try another one. So we're going to do the integral of natural log x over x. And first thing you want to think, is it just a basic antiderivative? So can I just look it up on my table, our table of elementary forms? Is it just the sum or difference or constant multiple? And this isn't. This is something different. So because it's not one of our elementary forms, it's not one of our basic derivatives or antiderivatives, we have to try the substitution rule. And, you know, first step of substitution rule, we're trying to pick u, and normally we're looking for parentheses, and we don't see any parentheses here. So it's not clear what the inner function is and you know, what the outer function is essentially. So kind of another strategy. So if you get stuck, and you know, you're going to get stuck on some of these problems when you do them, and that's okay. It takes practice, and sometimes integration can be difficult. It's not clear what method to use, and if you know to use substitution rule, it's not clear what you should pick for u. So another strategy for how to choose u is to kind of break your function apart into the different pieces. So I might write this as natural log x times 1 over x dx. And then I just look at the different pieces of my function. So first, I have this x in the denominator, so I might consider that a piece of my function. So maybe I would do u equals x. Maybe I expand my scope a little bit and say, all right, I have this as a piece of my function, 1 over x. So maybe I pick u equal 1 over x. Or maybe I let u equal the natural log of x, the other piece that we had up there. So you're just kind of trying to identify the different pieces of your function, and you go through, and where your choice for u really works is what happens when you calculate du. So you're going to be able to tell pretty quickly if things are looking good or if they're not looking good by what happens when you calculate du. And so this first choice for u here, we never do this one, u equals x. And the reason is because all you're going to do, you're going to end up with the exact same problem. Only difference is you're going to have u in it, but it'll be the exact same function you're trying to integrate. So you never do this substitution. So you'll get the exact same problem. You don't really get anywhere. So we never let u equal x. I mean, it's fine, but it doesn't get you anything. So what about that u equal to 1 over x? So let's calculate the differential. So derivative of 1 over x would be negative 1 over x squared, and then we multiply by dx. And we want to take that differential and we want to compare it to our integral. And so what we notice is if we look inside our integral here, there's no 1 over x squared. So what we can say is this differential is not a close match. Doesn't necessarily mean it's wrong, but it's not a close match, meaning we might have to do a lot of work to try to get it to fit. So try something else. So this 1 over x squared, when we have our integral here, we're letting u equal this 1 over x. We're kind of comparing the term in our differential to any of the extra terms that we have inside our integral, if we were to use that choice for u. So the 1 over x, that's spoken for. So what we have left there is natural log x, and that really is not a close match with the 1 over x squared that we see. So again, we might be able to get it to work if we did some algebraic trickery, but it's not very close, so we want to try something else. So one of our other choices is, all right, let's let u equal the natural log of x, and let's calculate du. So what's the derivative of natural log x? Well, it's 1 over x, and then we multiply by dx. And we know the natural log is spoken for. That's our choice for u. So that's good. And then if we look at the remaining pieces, what do we have remaining here? Well, 1 over x dx, and that's exactly what we see. So this is a very nice, good match. So this is a close match. Again, it might not be perfect, but this one actually is. So this is a close match to the remaining terms. So that means we're onto something. That means this choice for u is probably what's going to get us there. So this is just another kind of approach for how you should kind of think about choosing u, is to look at the different pieces of your function, and when you calculate du, you're going to see if things are going to fit together nicely or if they're not. So, I wouldn't do this for every single problem, but if you're kind of stuck on one, this might be the approach to take, is you look at the individual pieces of your function and just try them for u and see what works and what doesn't. So let's do it for real. Let's let u equal we're going to let u equal natural log x. So du then is 1 over x dx. Still helpful to kind of have it written with everything separated. So natural log x times 1 over x dx. We know the natural log term there, that's going to be our u. And we know the 1 over x dx, that's going to be our term for du. So when we go to step 2 and we fill all of this in, we're going to have the integral of u times du. So again, the natural log x term, that became our u, and the 1 over x dx term, that became our du. And so now we just need to do the antiderivative of u. So that's step 2. Step 3 is just do the integration. And so we use basic power rule, add 1 to the exponent, bumps us up to u squared. Take that new exponent, flip it, put it in front, so we get 1/2 u squared, and then plus c at the end. And then we want to convert back to our original variable. So the last step is to, wherever we see a u in our antiderivative, plug in what we said u was. So here we get 1/2 natural log x squared plus c. And that's step 4. Just a comment here about notation. You might see it in the literature, so like in the textbook or on our homework, you might see something like this written as natural log squared x. So, a lot of times we see that for trig functions. So like sine squared x, the squared is not just on the sine, it's on the whole thing. It's sine x squared. So sometimes you might see natural log x all squared written as ln with the 2 kind of on the natural log. Just means natural log x all squared. Just a little comment there about the notation, but I would leave it like this. All right. We're going to jump into, we're going to skip ahead, and we're going to come back to these. But we're going to jump into learning outcome I4 and just see how substitution rule works with definite integrals. And really, there's 2 ways of using substitution rule to calculate a definite integral, and very similar, same amount of work. One is you're just doing things in a different order, basically. So the first method, you're finding the antiderivative using substitution rule. You're not going to change the limits of integration. So you just leave them in terms of x, and then you're going to convert the antiderivative back to x, just like we're normally doing with our substitution rule, our u-substitution. Convert the antiderivative back to the original variable. And once you get back to that original variable, then you evaluate like normal. So this is our first method, is basically do everything that we were doing, and then once you have your antiderivative at the very end, then you evaluate for your definite integral. So let's try this out in an example. So let's do the integral, definite integral now, from 0 to 1 of 2x times x squared plus 1 raised to the power 5. And so we're going to do this using method 1. So basically, we're going to go through the substitution rule just as how we were doing it. And then once we have our antiderivative, then we'll evaluate. So let's see how this would look. So we have to pick u. That's our first step. And so we kind of identify the complicated term. And we see that that's something raised to the power n. So we're identifying our complicated term, and it's something being raised to the power n. So what we're going to choose for u is we're going to let u equal the term that shows up inside the parentheses. So we're going to let u equal x squared plus 1. Forget about everything else. We want the derivative of that. It's 2x. And to get the differential, differential du then is equal to 2x times dx. So that's the first step of substitution rule. Second step, we want to plug everything in. And as we go through this, I'm going to write my limits of integration as x equals 0 and x equals 1, just to remind myself that I'm not changing them. So I'm going to leave those limits of integration. I'm going to leave those in terms of x. So just to remind myself, I'm going to write them not as just 0 and 1. I'm going to write them as x equals 0 and x equals 1. All right, so now we want to convert this integral into u. And so that x squared plus 1 raised to the power 5, that's going to become my u to the power 5. And then I look at everything else. So I have 2x here, that's sort of an extra term. And I have my dx there on the other side. And if I compare those, well, it's nice. We have a perfect match. So the 2x and the dx, I can kind of combine those, and they form the du at the end. So I've substituted in u and du into my integral. Now I want to go through in step 3 and just do the antiderivative, just like we were normally doing. So I add 1 to the exponent, bumps me up to u to the power 6. Take that new exponent, flip it, put it in front. So I get 1 over 6 times u to the power 6. We're doing a definite integral, so I'm not going to use plus c. And since we're doing a definite integral, we put our evaluate line on the right there. So we put this big vertical line, the lower limit on the bottom, the upper limit on the top. So we're going to evaluate this from x equals 0 to x equals 1. Next step, we're going to convert our antiderivative back to x. So instead of u to the power 6, wherever I see a u, I'm going to change that back to x squared plus 1. So I'll have x squared plus 1 raised to the power 6. Still, we haven't evaluated yet. So we put our evaluate line. And once let me get that x equals 0 out of there. Move it up a little bit. And so that's basically all of our substitution rule steps. And then the very last thing is we just evaluate that antiderivative just like we normally would with a definite integral. So the top number goes in first. So we plug the 1 in, and we get 2 raised to the power 6. Then we subtract, plug 0 in, so we get 1 raised to the power 6. And that's step 5. That's our evaluation. Now we can simplify that. 1 to the power 6 is just 1. And then we could factor out a 1 over 6 if we wanted to. So the 1 over 6 goes in front, and then we have 2 to the power 6 minus 1, and we could even go further with that, but that would be fine. So, when you evaluate these, you want to be able to simplify the easy things. So, and this goes for just evaluating any definite integrals. 1 to the power 6, I mean, you could leave it, but it's better to get those things out of there. 1 raised to the power 6 is just 1, and we don't normally write multiplication by 1. Same thing with like zeros. If we have something times 0, don't leave that in. Just it becomes 0. All right, so I think we're gonna stop there for today. So we introduced the idea of substitution rule. And really, this is all you need to be able to evaluate a definite integral if you have to do substitution rule along the way. What we'll see next time is we're just going to do a bunch more of these. So we're going to just go back and practice more substitution rule problems. And then we will see one other way to handle definite integrals. And maybe I'll mention this really quick. And that's where we're going to find the antiderivative using the same u-substitution. So most of the work is going to be the same. We're going to do the same u-substitution. The only difference is we're just going to convert the limits of integration. So we're going to change our limits of integration from x equals to u equals. So it's just another way of doing these definite integral problems if you have to do substitution rule along the way. Really, it's the same amount of work. You're just doing things in a different order. So whichever method you want to use here is perfectly fine. You just have to be consistent. So sometimes, you might want to do method 1. Sometimes you might want to use method 2. And kind of the benefit of method 2 then is, since you've converted your limits of integration, you don't have to convert your antiderivative. So it's all really the same amount of work. It's just the order in which you're doing everything. I tend to prefer method 1, but it's easier just to kind of do all the integration stuff first and then just evaluate like normal, in my opinion. Once you start moving things around, it gets easy to make mistakes. But whatever you're comfortable with is perfectly fine. So we'll see method 2 next time. We'll do a couple examples involving method 2. But method 1 is really all you need to be able to do these definite integrals if you have to do substitution rule. All right. So next time we'll just get more practice with substitution rule. Like I said, this is a really important topic. So the more practice you can do, the better off you'll be. And then probably once we get out of lecture, I'll be posting the exam 5 results on Gradescope, so you'll want to have a look at that. If you have any questions, you can go through them with your TA during recitation today or next Tuesday, and then we'll stop there for today. So have a good weekend, and we'll see everyone next week. Bye-bye.